In the second video, I'd like to talk a little bit about the fundamental theorem of calculus. Now, the first part of the fundamental theorem of calculus, if we have a function f of x and a function capital F of x, and suppose f prime of x is equal to f of x, then f of x is an antiderivative of f of x, of lowercase f of x. And we know part of the fundamental theorem of calculus says that if we want to take the definite integral of f of x between a and b, in other words, if f of x were a positive function, it would give us the area under the curve. All we have to do is calculate the antiderivative of f of x and evaluate it at b, the top limit, and subtract the value of the antiderivative at the lower limit. That's a remarkable theorem, and it helps us solve a lot of problems. And so the idea here is to know the antiderivative. And you know how to do that for a lot of functions. Now let's change this a little bit and let's calculate the integral from a to x of f of t dt. Now notice this is just a definite integral, and we know that this is equal to f of x minus f of a. Now, suppose you wanted to calculate the derivative of the integral from a to x of f of t dt. Then that would be f prime of x minus d dx of the constant f of a. Notice that f of a is a constant. Capital F of a is a constant. But capital F prime of x, we already know is just plain f of x. So we have a fundamental theorem of calculus that also says that d dx of the integral from a to x of f of t dt is just simply equal to f of x. Very important thing to know. The idea here is that if you have f of t dt, to calculate the derivative of the integral with respect to x, all you do is put x where t is, and you have the answer. So that's like the second part of the fundamental theorem of calculus. Now let's look at a function, the integral from a to g of x of f of t dt. And now as we've said before, this is not just x. So we need the chain rule. So if we want to calculate d dx of the integral from a to g of x of f of t dt, we need to follow basically the same procedure and put whatever is up at the top everywhere you see a t. So we're going to do that. That's f of g of x. But we're not through yet. We need the chain rule. Since this is not plain old x, it's some u equal g of x, we need to calculate the derivative of g of x, which is g prime of x. Chain rule. I guarantee you we're going to have some problems like this on the final, and you'll have to remember the chain rule. So let's work an example or two. Suppose we have y is equal to the integral of a to x of sine squared of t times tangent of t dt. Now, here we have just plain old x, so dy dx is just going to be putting the x where you see the t, so that you get sine square of x times tangent of x, and you're done. But suppose you had y equals the integral from a to x of, let's say, cosine of 5t times 1 minus t squared dt, and you wanted to calculate dy dx, you get simply cosine of 5x times 1 minus x squared, and you're also finished. You put the x everywhere you see of t. Now let's do another one in which we have y is equal to integral from a to let's say ln of x, and we have that the function we're integrating is, for instance, sine of t times 1 minus t squared dt. dy dx is equal to, you take what's up here, it's not plain old x, but you take it and you put it everywhere you see a t. So we're going to get sine of ln of x times 1 minus ln of x quantity squared. So you replace the top number everywhere you see a t, but we're not through yet. We need to multiply it by the derivative of the top function, which is 1 over x. Remember, if y is equal to ln of x, dy dx is equal to 1 over x. Let's do one more example. Suppose y is equal to the integral from a to e to the x, and we're taking the integral of t to the fourth minus 5 sine of 3t dt. dy dx, take this e to the x, put it everywhere you see a t, and you get e to the x to the fourth power minus 5 sine of 3 e to the x. But you're not through, guys. Don't forget the top. You got to multiply it by the derivative of the top limit, which is e to the x. And we can do a little simplification of this. This is e to the 4x minus 5 sine of 3 e to the x, all multiplied by e to the x. Let's do another little wrinkle. Suppose you had y equal the integral from x squared to 3 of tangent of t squared times e to the t. dy dx, you can't just go on and do this because the variable is not at the top, it's at the bottom. So you need to write this first as dy dx is equal to d dx minus the integral from 3 to x squared. You need to flip the upper and the lower so that you have the variable at the top. When you do that, you know you have to take the negative of the integral e to the t tangent of t squared dt. So we can write this as minus d dx of the integral from 3 to x squared e to the t tangent of t squared dt. And since we now have this at the top like we want it, we go ahead and substitute x squared everywhere we see a t. So we get e to the x squared tangent of t squared, put x squared everywhere you see a t, and that would be x to the fourth. We're still not through. We need to multiply it by the derivative of the upper function, which is 2x. And then you could rewrite this as minus 2x e to the x squared tangent of x to the fourth. I think that's correct.